Hey yo, what's up guys? Baby Bear 4812 coming at you one more time. Leetcode 127 word ladder this time, and I'm laughing for two reasons. One is like I struggle with this problem. I think medium is deceptive here. I think this should be a hard. Uh, the other thing is that this is actually my second time recording this video. I forgot to press record the first time. So if you're here to learn how to get better at Leetcode, you come to the right place. If you're here to learn how to make good YouTube videos, get the hell out of here. So now that that's out of the way, let's start by noticing that Amazon goes trigger happy on this question. Facebook, Google, Lyft, you guys can read. You see it there. Like I said, this one's a toughie. And I know there's a word ladder too. I'll get to that one as well. But I think this one's tough. If you haven't tried it already, as always, give it a shot. Come back after. You know the drill. But otherwise, let's dive into and see how we can tackle this thing because it's a beast. It says we're given two words, a beginning word and an end word, and a dictionary's word list. We need to find the length of the shortest transformation sequence from begin word to end word, such that only one letter can be changed at a time. And the second condition is that each transformed word must exist in the word list. Okay? We're given a bunch of notes here saying we need to return 0 if there is no such transformation. So that's kind of how it sounds like error checking to me. All words have the same length. Cool, it's convenient. All words contain only lowercase alphabetic characters, fine. We may assume no duplicates in the word list, and begin and end word are not empty and are not the same. Cool, so no funny business. Now, to give you a specific example, imagine we had hit and cog as as our words, and we need to find out how to get from hit to cog by changing at most one letter at a time. With the kind of condition that one letter change needs to result in a word that is in our word list. In their example, the shortest way there is to go from hit to hot. So the I becomes an O, and notice that hot is in here. Hot becomes dot. Okay, so H becomes D. Dot becomes dog. Dog is in here. Dog becomes cog. Cog is in here. We're done. This is one of the shortest transformations. I'm sure there are others. Well, I know there are others, but this is one of them. We do not need to actually return the steps themselves. We only need to return the length of what these steps would be. So, a lot to digest there, but I think we can break it down into a couple of components. One thing to fundamentally notice is this: we're trying to get from one word to another. Okay, I'm going to move over to the whiteboard. We need to go from one word to another in the shortest possible path. Immediately, I think that should start to scream that this is a graph problem. And right off the bat, if you don't recognize that, I think that it'll be very difficult to proceed. I think there might be a way to do it with the prefix tree, or like a tree or try spelled with an I. Let me know down below if you have a nice, elegant solution to that, because I couldn't come up with one. But if you don't recognize it's a graph problem, you may be a bit hard pressed. The other thing that is nice to note is that we can kind of conveniently represent this as a graph, and I'd like to go ahead and do that here just to show you guys what I'm talking about here. So I'll start arbitrarily just from the word hot. It's the first one I have in my list here. And hot can go, from looking at this list, it can either become dot or it can become lot. In both cases, it's only the first letter that is changed. Dot here, looking at this list, it can become either a lot or dog, so it can become lot. It can also become dog. So again, I'm showing a graph just to visualize this a bit. Dog can either become a log or cog. I'll put log down here, and I'll put cog here, and so dog can kind of go there. And finally, or not finally, but lot, we know can go to dot, and it can go to log. Log can go to lot or dog or cog, and cog can go to dog or log. And again, I'm jumping through this a bit. Like I've looked at these before. If you pause the video and just look at the words, you'll see what I'm getting at and how I put this out. This is one possible graph. It is one part of an isomorphism of graphs for you graph theory fans out there. And what we'll notice is that this is actually an undirected graph. So no matter where we go, we can kind of traverse either way. And as well, it is an unweighted graph. And there's a reason that I say this. If we have an unweighted graph and we are looking for the shortest possible way to get from point A to point B, we can just use breadth first search, and that guarantees the shortest path. So that's nice. That means that, right off the bat, we can say, okay, so I'm looking to get to the end in the shortest possible way. It's unweighted, it's undirected, and namely because it's unweighted, we can just use breadth first search. And that's awesome. It's going to save us a lot of trouble. If this was weighted, if you're in a situation where you have a weighted graph and you need to find the quickest way from point A to point B, then you'd use something like Dijkstra's algorithm, in order to actually calculate that, because it is a bit trickier. But in this case, point one that we want to notice is like, okay, we want to somehow use, I was going to say utilize, but too fancy, use BFS. All right, so that'll be good. That'll get us part of the way for sure. Now, the weird part about this question, I think what makes it harder is this business of like, you can only change one letter at a time. All right, so how do we go about doing that? Well, when I did this problem a bunch, or I tried to do it a bunch, and I was timing out a lot, and one thing that I realized is this is a computationally heavy problem, meaning that there's going to be no way to get this down to like a linear time or anything close to that. So it will be, I think, like m squared times n or something along those lines. It'll be up there in terms of time complexity. So, we're not going to try to be heroes, although I think what we will come up with is the most efficient way to do it. Whenever you have something that's computationally heavy, and rather, let me take a step back and walk you through my thought process. The reason it will be computationally heavy is because if I'm at hot, I will have to check, okay, let's say I'm at hot here. What happens if I drop the H? I only look at OT. And then I need to look at every other word that only ends in OT. All right, I'm going to do this here. Then I'm going to do the same thing with the O. Then I'm going to do the same thing with the T. And I'm going to do this for every word. No matter where I stop, I'm going to keep repeating that same calculation over and over again. And that's a lot of work. Okay, that's a lot of complexity, a lot of space, a lot of time. One way that we're going to go about doing this, and I think this part is I'm not sure that it's very unintuitive, but I don't think it's obvious, is that we can do some pre-processing to speed this up. So the one of the big tricks here, I'd argue, is to recognize that there is some pre-processing that can be done. And I'm going to tell you exactly what I mean by pre-processing. This calculation that I just described, if we can do that once up front and create some sort of dictionary, so an instant access structure to actually figuring out, if I'm at hot, where can I potentially jump? That'll save us some headache down the line, and it's essentially one of the keys to solving this problem. Let's think about this. What I'm going to do is I'm going to represent all the possible variations of hot using wildcards. And when I say variations, that will mean only removing one letter and replacing it with any other possibility. So what I'll do is I'll say, imagine we had this dictionary, and I'll say that this can be one of my words. It can be, this is a pathetic attempt at an asterisk, OT. Okay, and from there, we're going to have a list of words that we can go to. I'm also going to have H asterisk T, and that'll yield me another list. And finally, I'll move this down a bit, H O asterisk. And from here, what I'm going to do for each one of these prefixes, not even prefixes, but I'll call them wildcard words, I'm going to look through my list and find out what word fits this combination. Okay, and when I say fits this combination, means there's only one letter off. So these two match, and the star can be anything, and these two match, and the asterisk can be anything, and you know what I'm getting at. Well, if I look through this list, the words hot, so the word itself, as well as the words dot and lot, which I just drew right here, all will go in here. This means that when I'm sitting at, oops, wow, that was dot. So I think what's happening is my computer is really pumping away. As I've told you guys before, this is a 2013 MacBook Pro. Like I don't have much horsepower on this thing, so that's why it's a bit slow and the writing's all awful. From here, there's no other words that fit this kind of template. So this will only be the word hot, and also again only the word hot. Wow, that's brutal. And there we go. All right. The reason this is going to help us is as follows. And by the way, I've only done this for one word. We're going to do this for all 6 of these words, so they would, in this case, be 18 entries in this dictionary. What this is going to allow us to do is when we step on this node hot, when we go through our breadth first search, we will recognize that, okay, this word has 3 possible wildcards. For each of these wildcards, let's look up where we can go. Right? Can we go to hot? Can we go to dot? Or we can go to hot, we can go to dot, we can go to lot if we haven't visited them already. Right? That's going to be a condition that'll kind of help us break out earlier if we need to. But that's essentially what the logic is going to be here. If I can pre-process the possible paths from the place that I'm standing here, and then that's how I'm going to be building my queue. The part that takes us a layer deeper here that may be a bit less intuitive is it's not just about saying, okay, I'm at hot, where can I go next? If I'm at hot, I can either go to a certain amount of places if I'm at star OT, or if I'm at H star T, or if I'm at HO star. And of course, as the words get longer, there are going to be more and more of these combinations. And so Without doing this pre-processing, we'd end up in a lot of repeated calculations that would be very messy, and that would likely time us out. So this is the the second part to the problem here, and I know I said this was a tough problem, and it is. I still do believe it. It's a bit misleading, in my opinion. It's honest, but seems misleading to say this can be done if you just understand that there are two major chunks happening in this problem. But that's the truth of it. If we can understand how to pre-process, make this dictionary, and then do a standard breadth first search, that's actually going to be enough to make this problem work. And again, it's one of those weird ones where I see a lot of people struggle with it. I still think it should be ranked hard. Apparently, a lot of people in the discussions agree. But when we really break it down, there isn't all too much going on per se. That said, I think we're in a good spot now where we can pause. I was going to say pause the video. We don't have to pause the video. We can keep recording the video, but pause out on the whiteboard explanation and jump over to the code and see what that will look like. So, this out of the way. Couple points here. First thing we're going to want to do, I'm going to move this over just so my big head isn't covering the code. I'm going to do some error checking. As per usual, I'm going to do our pre-processing. We are going to do this together. Then we're going to do the BFS. And within this breadth first search, remember I said that if you're doing the BFS, you will get to the shortest point by default if you ever hit it. At that point, we just return our value. So if we never get there, if we never return anything in this BFS, we haven't found what we're looking for. Kind of like you2. And then we return 0. So that's where we're going to have that at the end. And I didn't get into the minutia of why that works, but and I would urge you, if you're curious to do a Google search, that will give you a much more explicit and thorough explanation than the 30-second soundbite I'm about to give you. But basically, if you imagine when we're doing a breadth first search, imagine like you drop a little pebble in a pond and it kind of ripples. Okay, so you'll get this one maybe little ripple right here, and then that ripple it'll grow into something. Oh, I'm sorry. That'll grow into a bigger ripple, which will cover these two over here, and then the bigger ripple, which visually will cover log and dog. And then eventually what's going to happen is, since we're going out kind of one layer at a time, the shortest possible layer with almost a diameter, if you will, that'll hit this node is going to be by default but the shortest path to actually getting there. That's just a quick visualization to make a bit of sense out of that. Anyways, I digress. In the error checking, I'm just going to make sure that we've actually been given all these. Okay, that's one thing. So if not begin word, or not end word, or not word list, or here's a sneaky one. So when they try to pull on you, and you see it in the example here, they might give you an end word that's not in the list. So, or end word not in word list, then we're going to return 0 because it's not possible. Really simple error checking, okay, nothing to write home about there. Now, we're actually going to do the pre-processing here. And what I'll do is I'll call it processed words equals, I'm going to call a function here just to modularize our code a bit. I'm going to write it out separately. So I'll call self.preprocess the word list, please. And let's go ahead and write that out super quickly. Not too quickly, but quickly enough. Where we're going to define pre-process, and we are going to put in self and the word list itself. So we're going to want some dictionary. I'm going to call it D for sure. I'm going to want to return this dictionary when I'm all done with it. And what I'm about to do, itchy nose. This happens a lot when I record. I don't know what's wrong with it. It's like a mental thing. What we're going to want to do is, what we're about to do, there is a way to do with default dict, I believe. So for those of you who are familiar with it, go nuts. I like to keep these videos for the most part down to first principles, just so the code is really accessible and understandable no matter who's viewing it. What I'm going to want to do is for every word in the word list, I'm going to want to, at every step of the way, create this wildcard. So I want to drop one character systematically at a time. So I'm going to say for C in range and the length of the word, I'm going to want to create a wildcard. And I'll say that wildcard is equal to the word that goes up to this character C, up to but not including. And then we're going to replace that with some sort of asterisk. And then I want the next character onwards. So I'm going to a word of C+1 all the way until the end. So if I want to drop a character C, I'm going to go up to that character but not include it. Instead of that character, I will add an asterisk. And then from there, I will add the next character onwards. And that's going to create my wildcard entry. I'm then going to say if the wildcard is not in, I don't need the word is. If wildcard not in D, then we're going to want to say d of wildcard is equal to some empty array, because what we're going to do, if it is in there, or even if it wasn't and now it will be, we're going to say d of wildcard dot append the word. So if I'm dropping one letter, then I'm going to want to append the word onto that wildcard, kind of like how we did here with hot. Right, so hot was in there, and then every time I come across another word when I'm creating wildcards, if it's only that one letter off and the wildcards match up, if you will, we're going to append that full word into that dictionary entry right over here. And that's it. This is actually all that our pre-processing is, and that will create this structure exactly for, in this case, all 6 of our words, 3 letters apiece, so our 18 entries. So we have that pre-processing done. That's arguably half the battle, maybe even the harder half, because the breadth first search for the most part is just a standard BFS with maybe a couple of small tweaks, but nothing to write home about here. Within the actual BFS, we're going to want to do a couple of things. First thing we want is to actually create a queue. I'm going to use the built-in deck library here. I know maybe that's contrary to what I was saying earlier up here about not using the built-in libraries, but I feel like it would be overkill for this video to build out like the nodes and the doubly linked list and make all that from scratch, because that's not the purpose of what I'm trying to do here. So I'm going to be using the built-in deck. I didn't spell it right. And we will, and by the way, that is pronounced deck. It's not, I thought it was DQ. The documentation says it's deck. So yeah, in the queue, I'm actually going to want to append our first word. So I'm going to say begin word. Now, there's one other thing that I will want to append for the following reason. As we're going through this BFS, if we find the word that we want to find, we want to have somehow kept track of the length or the amount of steps that we've taken in order to get there. The easiest way to do that is just to put this in some sort of tuple or an array. I like to put it in an array. You can use a tuple if you'd like, and start by inserting the word 1, because we are on our first transformation of this word. In the question, the way they described it and how they went through the examples, this would actually count as legitimately being the first transformation onto the word itself. I would argue logically, I would put a 0 here. I think that would make more sense. We haven't done anything with it yet. But following the instructions and the examples, that's how the math is going to check out. So it is what it is. Like, as you can see here, when we went from hit to cog, we had 1, 2, 3, 4, 5. So this word itself counts. That's why I'm starting from the 1 here. I'm then going to jump into the standard BFS stuff, which is while queue. So while we have any sort of items in the queue, let's make some stuff happen. I'm interested in finding the current word that I'm working with, so that's going to be cur. And what I'm going to do for that is I'm going to pop out from the left side of this queue. I'm going to pop that first item in. So if you can picture the queue on the leftmost side, that's kind of the head of it. That's what I want to take off, right? Otherwise, I would just say pop if I wanted something from the end. What this will pop out will actually be an array. In this first iteration through this loop, it will be this array here. So what I'll do is I'll actually just destructure this immediately and grab both the current and the level that we are at. Again, the level will be needed because we may be returning it if we find the end word that we're interested in. Now, couple things. We need to say the following. We've got to say, for this word that we are on, so for example, we're on hot right here. Actually, you know what? I think there we go. We're on hot right now. For hot, I need to check all the possible paths that I can take to jump out of this node. The possible paths that I can take exist within this pre-processed array that we created. However, what that does mean is that I'm going to need to check every wildcard here. Okay, so once again, I'm going to be borrowing this code and saying for C in the range of the length of cur, in this case, I'm going to want to create a wildcard. And that wildcard, they'll be the same as the ones above. And what we'll be doing is we're just going to be checking if this wildcard is in here, then we can potentially make some movements. So if wildcard in processed words, then we're going to want to, do cool stuff. So the reason I'm checking this here again is because maybe not, maybe I'm overkilling it here. Let's see, if I'm honest with you, this if statement might be overkill, but I want to make sure that I'm not going to get a key type error if for whatever reason the wildcard isn't within the processed words. If the wildcard is in the processed words, then what we want to say is the following. We want to say for word in processed words at that wildcard, we got just enough space there. Let me move this over a bit more. we want to look at every word in this queue. So for example, we've got all these words here that we want to look at. So I'm going to loop through each one of them. There's one thing I missed here that I'm going to add in a moment. But I want to see the following. I want to say if that word is actually equal to our end word, then we're done. Then we're just going to return the level that we are at plus 1. The reason we're adding the plus 1 is because, again, if we started at a level 1, that was our initial word, we then made a change. We're making a transformation. We're taking one step further. I haven't taken that account yet into my level, so that's why I'm going to return level plus 1. Otherwise, if we haven't visited this node already, and the one thing that I forgot to add in here was some sort of scene or visited set. So maybe I'll call this visited and make it a set just so we have that instant lookup. So what I'm going to say is if the word is not in visited, then we say the following. We're actually going to add it to visited because, okay, we've been there. And then what we're going to want to do is add it to the queue. So we're going to say queue.append, and again, we're going to put the word in itself, and we're going to want to include its respective level. This word is one transformation up from the level we were currently at, and that's why, again, we're adding the plus 1 here, kind of like we did over here. Maybe I'll leave that. I'll format the spacing so it's all unique. And that should be it, guys. If I haven't missed anything, that should actually give us everything. If it was visited, we don't do this. Otherwise, if we go through this entire array, we've never returned anything, we will return a 0 because that path was not possible. I'm going to press run here and make sure I didn't make any typos. And as always, I did. I made one on line 29, and I called it word instead of calling it cur. This should have been cur. Okay. This should have been cur, and then the rest of these are all word. That should be good. And I'm just going to submit and make sure that I didn't miss out on anything else. Cool. And you see the results there. Super good speed, and memory usage not so great. I'm not sure how we could have fixed that. But regardless, just to recap, and I'm going to make sure, there we go. You can see all the code and the screen fits perfectly. I don't think it's an easy question. I don't even think it's a medium question. But I think it's doable. Fundamentally, you need to begin by understanding that this is a graph problem. Without that, it's going to be really difficult to proceed. When you realize that it's a graph problem, you notice that it's an unweighted graph, and that means that if they're asking for the shortest distance, which they are, we can use breadth first search. On top of that, if you can notice the kind of this wildcard pattern and realize that we need to check all these combinations, and there's a way to speed that up slightly by doing a lot of the calculations and on a pre-process, like ahead of time, in an ahead of time way, and be mindful of that. That's going to be the second part to understanding how to get this thing done, and that was, again, this method that we wrote up here, this function. I hope this video helped. I know this question has caused a lot of confusion. I've seen some videos of it up already. I struggle to understand a lot of those videos. Not all of them, but for the most part. So I was hoping to make something that would be a bit more digestible and a bit more understandable to get you over the finish line with this one. I hope it helped. As always, like, comment, share, subscribe. I'm not going to tell you what to do anymore. I probably will, but I don't like to. But, if you could share, that would be awesome. Yeah, I think your uncle needs to see this one. I think that's what the word on the street is, so don't forget to show him. And yeah, any questions about this, let me know down below. Anything else you want me to do, also let me know down below. And I will see you guys next time. Peace.